Good afternoon, everybody. Welcome to the webinar on coatings and corrosion. Thank you very much, Akshit, for this elaborate introduction. And thank each one of you for dedicating a valuable 1 hour during a working day to participate and try and understand what we are doing in terms of coatings. So the whole, it's just a brief background of our marine and protective and yacht coating business, the way we are positioned. Our business units, if you look at it at a glance, in marine, we have segments like new construction where new build ships are being coated, deep sea dry docking where the bigger vessels which travel between continents and countries, they have a business in terms of dry docking and sea store supplies. And of course, the coastal and navy, the coastal business in terms of the smaller barges, smaller vessels, and the naval vessels, especially Indian Navy, Sri Lankan Navy, Bangladesh Navy. So we do have these business strengths. Protective coatings is a huge business. We have starting with oil and gas upstream, oil and gas downstream, heavy industry, OEM, high value infrastructure. So the whole range of businesses or industries are covered, including windmills. Yacht, we have do-it-yourself market, the smaller luxury boats, then you work with professional applicators, then you have retailers who sell our yacht coatings, distributors who work with us very closely and the customers to ensure supplies are in place. And of course, the very rich and very expensive super yacht business, which looks at extremely high level of finishes and quality and performance. That's how we look at our businesses in MPY as a glance, at a glance. And when I look at the agenda for today, we are talking of some little insight into basics of corrosion, talk a little bit on basics of paints. Then, of course, how do you specify these coatings onto the customers? What is the basis of this particular specification? Why the coatings are recommended in that way and in that thickness? What is the background? Then we look at a few slides on coating application. What is so special about this coating application when we look at high performance? Is there a special method of application? Why do you do it that way? Then we'll also talk about a little bit of coating defects. Coating defects is a huge repository on its own. I cannot talk of every defect. Every day you find a new one sometimes. So it's a constant learning. I'll talk of some very basic defects on the background of those defects so that each one of you will get a flavor of what to look forward to when coatings are applied with a sharp eye. Then, of course, there will be a Q&A session, open house, moderated by Akshit, our moderator at this point in time. When I define corrosion, corrosion is nothing but you would have seen rusting or deterioration of any substance. And here we are talking usually of a metal. Why it happens is the metal loses its properties because of its interaction or reaction with the environment. What you should know is there is a material, preferably a metal, and it constantly works with the environment. It reacts with that, and thereby there are changes. In case of the metal, we normally look at deterioration. If you look at the picture, you would find steel loss. You could find steel loss here. You could find rust. You could find pitting. You could find issues in terms of structural integrity. So what we are trying to talk is corrosion is not just a superficial brown layer of rust. It has huge impact in terms of structural life and integrity. So corrosion is a constantly evolving interaction between the material and the environment, and it is causing a deterioration of the substance. So you should be very, very closely watching on this phenomenon called corrosion. The moment a metal is evolved or developed or delivered or even created or fabricated or processed, the moment it exposes itself to the environment, there is a deterioration, and that is corrosion. Keep in mind. Corrosion, how do you describe it? By looking at the results. For a common man, when he looks at corrosion, he'll see rust, and that is the result of which you'll say it is corroded. Maybe he'll see spitting, holes, or loss of thickness or dents. It's called loss of integrity. So corrosion is detected like that. It acts on engineered metals, usually metals. Engineered materials means created materials, for example, steel. copper. All these are engineered materials. So when we have engineered materials, it does have affinity to get corroded. Most common product of corrosion is iron oxide or the rust. It is brown or brownish red or reddish in color, sometimes even black in color. And this changes color with the presence of concentration of oxygen. For example, if you react the steel in very high concentrated oxygen environment, the rust would look possibly reddish. Low concentration of oxygen, it will look blackish. So keep in mind. So even if you find some black rust, it is certainly iron oxide, but at lower concentration of oxygen. Now, how it looks is it's a reverse of the steel manufacturing. How is steel manufactured? You take iron ore, you reduce it in a Bessemer converter or a furnace, and that's how steel is formed after alloying. But in this case, steel corrosion it's at steel, it reacts with oxygen, becomes rust. Rust is nothing but an iron oxide. So you started with iron oxide, you created steel, it rusted, became iron oxide again. So that is how the whole process is. Corrosion is the reverse process of steel manufacturing. Keep in mind. When we look at corrosion as a process, you should correlate it to the what is happening in a dry cell battery. What is happening in a dry cell battery is current is being delivered because of corrosion in a particular place or a particular part of the cell called the anode. So when the battery dies, that means the anode is completely dissolved and corroded. That's why there is a current. As long as the battery is in working condition, the anode is active and it is delivering a current. So similarly, like a dry cell battery, which has an anode, which has a cathode, in this case carbon, an electrolyte, there is a zinc paste inside, zinc salt paste, which acts as a conductor. And once all these things are come together and it's connected electrically to complete the circuit, you have electricity that is being delivered, which is used for various purposes, starting from your mobile, electric torches, various purposes it is used. So a corrosion process, an analogy is a dry cell battery. Keep in mind. A corrosion cell again has the same components. You can see an anode, you can see a cathode, you can see a metallic pathway in which anode and cathode is connected, and you can see an electrolyte which is surrounding the anode and cathode. In case of corrosion, the electrolyte can be the salts present in the environment, which is dissolved in the humidity. Humidity content of the air, that is water in the air. And it has got, once these two are connected, anode and cathode, and there is an electrolyte that processes or it accelerates the rate of corrosion, then you will have an electron flow, then you'll have a current that is created, then there is also an ionic current in which the anode dissolves and goes towards the cathode to strengthen the cathode. So it is just like a battery. Keep in mind. What are the components I was telling you? Anode, the part of the metal that corrodes. It dissolves in the electrolyte. A cathode is a more noble region in which the electrons are consumed. So when an anode releases an electron, it goes to the cathode and sits there. Then the return path of the metallic pathway is the conductor between the anode and the cathode. Metallic conductor where current can flow. And electrolyte is the liquid or the moist medium through which an ionic current or the exchange of ions happens. So what we should know at this point in time is, in order for corrosion to occur, all the four of these components should be available at the same time: anode, cathode, metallic pathway, and electrolyte. If one of the components is removed, then the corrosion will not occur. For example, you may have an anode and a cathode, but if there is no electrical conductivity, a metallic pathway, then it will not allow the corrosion to happen. So one way of protecting structures and against corrosion when you have different metals connected together is to insulate in between, so corrosion doesn't occur. Suppose you have a metal and that is exposed in low humidity levels. For example, relative humidity is less than 40% or 30%. The rate of corrosion falls drastically. That is a way in which corrosion also can be prevented or controlled. So understanding of a corrosion cell is very important. When you look at, I was explaining to you, there is something called an energy mountain, when the rust, for example, 18% of Earth's crust is filled with iron oxide or iron ore. You can see India is very rich with iron ore. Several countries in Africa, other places are rich with iron ore. It forms 18% of Earth's crust. So it doesn't deteriorate so easily. It's a very stable mineral or a ore that is available. It doesn't deteriorate. But what we are doing, you're using this bulk available raw material, heating it up. That means you are putting energy inside and converting into steel. The moment you pump something with energy, it becomes very active, It becomes very active, and steel becomes very active. Once this metal steel is active, it has got opportunities to react with the environment. It reacts, it participates in the reaction, and the natural tendency for any material when it is hyperactive is to go back to its normal condition, to come back to its lower energy levels. So when steel corrodes, it will again become rust and it will become a very passive material which is available. So there is an energy difference between the raw material that is used and steel, and the preference of that higher energy to react is what is causing this corrosion. So keep in mind that steel is a very high energy consumed material which is very active, and it will constantly corrode. There is no way you can prevent steel from corroding if the anode, cathode, metallic pathway and the electrolyte are available. It is a natural process. How to protect steel? Several things have happened, that steel, if you are to protect, they tried various things like metallurgy, how to sort of make very structured alloys which will protect itself from corrosion. So tailor-made alloys, for example, stainless steel is a tailor-made alloy. You take carbon steel, you dope it with your chromium, nickel, so you get various kinds of steel. So they have higher resistance to corrosion. Titanium is used. And then if you want to have zero corrosion structures, titanium-based structures, titanium-based steel, pure titanium-based structures are, but they are very expensive. For example, 1 meter of a titanium pipe 4 inches may cost you lakhs of rupees. For example, 1 meter of a carbon steel pipe may cost you thousands possibly. So that is the difference. One place which is close to us back down here is that iron pillar in Delhi. Whoever has gone to Qutub Minar, it is corrosion free for the last 1,000 years. Lot of work has been done in terms of trying to find out what is the reason. They have taken small pieces and they have found that it contained very high phosphorus content. Several theories are there. Even today, that is an embodiment of corrosion resistance. You can have a look at it. Just shared an example. Now, how to protect steel against corrosion other than by metallurgy? Because metallurgy is very expensive, you could do cathodic protection, a simple technique of corrosion protection of metal by making it a cathode. So if the metal becomes a cathode, a noble material, then it will not react so easily and it will protect itself. So make it a cathode is one way. Using sacrificial anodes, you connect it, you metallically connect it with anodes which can sacrifice itself. For example, zinc, aluminium, magnesium anodes, if it is connected, then that will preferentially corrode by protecting and thereby protecting carbon steel. So that is a cathodic protection. Keep in mind, some of them are bolted, welded onto it, and sometimes what is more important is it should be in electrical contact. There should not be any barrier between the anode that is connected and the surface. So this anode being more reactive, zinc anode being more reactive, will corrode itself. So you can look at this small picture where the arrows are pointed out. You can see the anodes in the ship hull where they have put it in close to the rudder area. A closer look, corrosion, the steel is protected and the zinc is corroding. Similarly, it happens on the legs, razor legs of oil platforms, several structures, tanks, everywhere they use this as a backup or a support system for corrosion protection. In steel, you will find all the components together. Steel is a non-homogeneous material. That means you will find areas of variable current potential. For example, you can find anode and cathode together very close by on the same steel metal sheet or metal pipe or a rod or whatever is the metal structure. So steel is conductive. You also have anode and cathode. Now, this is a very good potential for corrosion because environment contains oxygen. There may be humidity, there may be salts. Easily it forms an electrolyte. So steel becomes very active from the moment it is manufactured. At high temperature, steel corrodes in the casting yard itself, and that bluish gray surface which you normally look on brand new steel is nothing but a metal oxide which is hard. That is nothing but mill scale. So as it comes to lower temperatures, at lower temperatures the reaction happens with different levels of oxygen. Then you would have red rust and brown rust and all that. So steel is a non-homogeneous material with anode and cathode on the same surface, and only it requires a little bit of humidity, salt, and the electrolyte is formed. Corrosion is very active. Factors that affect corrosion, I was telling you, oxygen. Higher the oxygen, higher is the rate of corrosion. So keep in mind, temperature, it gets accelerated because of increasing temperature. Corrosion X, you heat it up, the rate of corrosion increases. Chemical salts, because it can form electrolytes, it will accelerate the rate of corrosion. For example, pure water, distilled deionized water, you immerse an iron nail, it will not corrode easily. But you add a little bit of sodium chloride or salt inside, it will corrode very fast. In your houses also, in kitchen, you don't notice salt is stored in plastic containers, you use a plastic spoon. Even if you use a stainless steel spoon in your kitchen for your salt, it starts corroding. Keep in mind. So we normally use plastic stuff there. Humidity or wetness, the atmospheric water saturation that is available will accelerate the rate of corrosion because it can easily dissolve salts inside, and that will cause an electrolyte. Pollutants are another huge issue. Pollutants will have acids inside which can convert to salts and accelerate the rate of corrosion. So keep in mind all these are factors that can increase the rate of corrosion. Whenever we have corrosion, there are several methods of corrosion protection. We are seeing cathodic protection was one way. Then we have also coatings. You have coatings which are applied on steel to protect against corrosion protection. Now, how does this work? How do coatings protect steel from corrosion? There are three methods. One is called cathodic protection, in which the coatings have sacrificial anode-based pigments. For example, zinc dust is added in coatings that will act as a sacrificial anode. When this paint is applied on the surface, zinc will preferentially corrode, thereby protecting steel. Then we'll have an inhibition process on the surface where we have specific inhibiting chemicals which are added in paint, which will react with environment and form a layer on the surface which will cover the complete steel, that exposed area, both the cathode and anode, thereby creating a barrier. That means it doesn't allow further penetration of atmospheric humidity and oxygen inside, protecting against steel. That is inhibitive protection. Then barrier. An analogy for barrier is like a raincoat which you wear on during your rain. Barrier is nothing but a thick layer of paint which is applied, which doesn't allow external contaminants to pass through in a very physical way, like a raincoat which protects your skin from wetness from outside. This barrier-based protective system will have a thick layer of paint which will protect it from exposure to external environment. So whenever we protect steel, it is not a permanent process. You may have multiple levels of protection, but it also has got a lifetime. Keep in mind, the life is about the process called durability. By applying coatings, what you're trying to do is protect it to the best possible way so that it slows the corrosion down. It doesn't stop it, and which will affect over a period of time is the kind of environment in which you expose, surface preparation of the surface. That means steel has got a lot of contaminants. I was telling you, oil and grease, surface salts, mill scale, rust. You will have seen that on steel. Now this has to be cleaned in a proper way. That is a surface preparation process. Once you clean it properly and apply a coating, the durability increases. So it's very important. One of the things you should keep in mind is you may have a good can of paint. You may spend a lot of money on getting the right kind of equipment, but if the job of surface preparation is not done properly, you could have huge coating failures. One of the statistical things that come to play is that approximately 70 to 80% of coating failures are because of poor or inappropriate surface preparation. Keep that in mind, that surface preparation is a very important method. Then we'll talk of methods of application. It is like transferring a can of paint into a coating film on the substrate. It's very important. If you do it properly, then if you cover the areas, if you apply the right thicknesses, use the right methods, of course, the protection levels will be much higher for a longer durability. Then achieving the right thicknesses. So there is a specification, there is coating thickness. It's a very important part. That's called the DFT, dry film thickness, which is what is a market analogy. So the film thickness is a critical characteristic of paint performance. You have to achieve the optimum recommended specified thickness in order to protect it to the expected durability. Keep in mind. What is this high performance coatings? You are working with International Paints and AkzoNobel. There's a brief history of this high performance coatings. When did it come to play? Anti-foulings for ships came into play in late 1800s. But if you look at the true high performance requirements, it started in 1930s. In the First World War, if you see Europe, a lot of the war was lost not because of people being killed, because of corrosion. A lot of bridges were corroded, it collapsed when heavy equipment went in. So then they wanted to find out newer methods of corrosion protection. So by 1920s, this epoxy resin was synthesized, which was supposed to be a strong, even now it is a very strong input into corrosion protection requirements. So in 1930s, they started developing paints based on epoxies, and that's what was used in the later years. It continues to be used. Started in 1930s. Decorative coatings which you use in your houses for painting your walls and wooden structures, they are generally used for aesthetics. Aesthetics is nothing but decorative purposes. High performance coatings to prevent corrosion and erosion of substrates, which has large industrial applications. It is generally applied on very large substrates and typically not for finish requirements. Of course, nowadays there are a lot of finish requirements also that is coming in terms of, it may not be like an automobile finish, or a domestic appliance finish, but it will give you long-term performance. Used in most industries where corrosion is a factor. So whenever we are selling our coating, we are talking to customers who are really affected by this phenomenon called corrosion. So that is one way. Painting, for what do you use? Corrosion protection, primary. Fouling control in ships on the hull we apply due to what happens in the ships is that you have all this marine growth, marine animals which stick onto the walls and reduce the speed, increase fuel consumption. So we use specialized paints to reduce this kind of a interaction. Then cosmetic appearance, colors, differentiators. Then we use linings for cargo contamination prevention. Huge tanks coated inside, for example, petroleum carrying tanks. Food cargo carrying tanks. Internally, it should be coated in order to avoid contamination. Abrasion resistance. When you move equipment on a painted surface, it should not get damaged. Non-skid properties. Keep in mind, whenever think of an aircraft carrier where you have planes landing on top of aircraft deck on ship decks, that should be a very rough surface which gives you grip and friction. Non-skid properties. Radar attenuation. For example, some specialized equipment or specialized vehicles, for example, aircraft, they are applied with specialized coatings in order to reduce the radar signature so that they cannot be detected. Of course, heat resistance, high heat, high corrosion. So in order to reduce corrosion impact at high heat, use heat resistance paints. So several new requirements have also come in. Some pictures for you. You can see it has gone to even your roller coasters, you have your oil and gas platforms, you can see fouling under ships, cargo tanks, aircraft carriers, refineries. So whole range of objects it is being used. What is paint? Paint is a liquid material applied to a solid surface which gives you a dry and continuous film which is strongly adherent, which will not break down easily, and which is designed to perform a specific function. The specific function can be corrosion protection, fouling control, radar attenuation. In the previous slide you saw various functions are there. What are the components? What is this can of paint containing? It's a mixture of so many things, you have a resin, a sticky substance on which you add a pigment, you have some solvents, and you have some special additives which are added in order to, and these are blended together under high energy, in the sense it is like dispersing. For example, one analogy for a dispersion could be what you use in your kitchen, a kitchen mixie. Whenever you add some component to the mixie and run that, it runs at such high speed, it breaks down the particle and disperses, makes it homogeneous. So that is the kind of equipment we use for manufacturing of paint, in which there may be multiple contents, some things which are volatile. That means it evaporates when it is exposed to the atmosphere. Solvents are volatile substances. And something that is non-volatile, that remains on the surface. That is the actual paint which you see once the paint dries up. That is the solid material which remains on the surface. Coatings are a combination of these two. Example for resins, it could come in various colors. Colors means it could be transparent white to slight brownish. One of the greatest characteristics of this is that it is the backbone of any paint performance. It gives flexibility, it gives adhesion, it gives flow, it gives gloss. It also gives corrosion protection properties in terms of resistance to chemical exposure. So it's a very, very strong input into the paint. Look at pigments, color giving matter in terms of powder. It could come in various colors. For example, one of the most used colors you would see is white. It's a pigment called titanium dioxide. Then you have black, which is carbon black. They use carbon black also in that. Then red oxide of iron. Yellow oxide of iron, and there are also synthetic pigments which are manufactured from organic synthesis. So they are color giving matter which imparts color. It gives you opacity. It gives you the ability for the paint to cover the base. For example, on wood, if you apply, wood looks reddish brown in color. If you want a green color on top of that, you add a green pigment in the paint which covers the surface. So its ability to cover the surface. Anti-corrosive properties. Some pigments are there like zinc phosphate, zinc, which act as inhibitive or sacrificial pigments. So they protect steel by reacting. Then these pigments also fill in pores within the paint to reduce permeability. Permeability is ability for external contamination to pass through. Then it can modify properties like spray and gloss. Of course, some of the pigments, when they're added, it reduces cost. These pigments are called extenders, which reduces cost. Most critical thing all of us know whenever paint is used is, do we have solvents and thinners? Solvents are expensive. It is a part of paint. It's used in paint to make it easy to manufacture, and it is also added in paint so that it can be easily applied. But they are environmentally damaging and waste products, because once you add a solvent in paint and thin it, and once you apply the paint, what happens to the paint is that the solvent evaporates. It's all lost in air. What is left back is what you pay for. But you are paid more because something went in air. So they are generally called waste products. However, with the present technology, we have solvent-free paint, but not for everywhere they are using it. We still use solvents in a large quantity. Easier, okay. Additives, they are added in small quantities in the paint. This is to modify the properties of the pigment and the resin. So they can challenge, or they can modify drying time. They can increase the hold up in terms of building thicknesses, higher thicknesses. They have the capacity to hold up the paint so that higher thicknesses can be built. Then generally a high performance paint has got a lot of pigments and heavy materials inside. It has a general tendency to settle. So we add some thixotropes or some special additives so that the paint can remain homogeneous for a longer time. Some additives are added for increasing dispersion, increasing the flow. In this picture, you can see sag here. This is the hold up part of it. Now there are additives. When we add additives to this liquid paint, this phenomenon can be reduced. Now in terms of cathodic protection, you always should remember that metals are reactive based on their ability to react with the environment at a faster pace. So when we are looking at electrochemical series, you have gold. Why is gold so expensive? It's got its decorative purpose. It doesn't easily corrode. So gold is at the bottom, least corrosive. Then you have stainless steel, which is more corrosive. Copper is more corrosive than stainless steel. Then you have carbon steel, which is much more, which is used in a large quantity. Then you have aluminium, you have zinc and magnesium. So as you go up this chain, the rate of corrosion increases. So when you look at steel in the center, if steel is protected by a material which is more reactive, for example, zinc, then steel can perform for a longer time. And this method of applying zinc or applying a more reactive material on top of a lesser reactive material to protect it is called cathodic protection. Here zinc is a sacrificial anode pigment. Normally, where all do you find zinc usage? You can find usage of zinc as in hot dip galvanizing, where you pass the steel through molten zinc and you have galvanizing that happens on the surface, where the layer of zinc on top reacts with the environment, protects steel. Similarly, you can add zinc in paint and zinc rich coatings are applied. So keep in mind, cathodic protection is one method of protection of steel. When cathodic protection methods are applied, this is at the electrical contact. That means the material of construction, that is steel, should be in direct contact with that zinc. That means it should be the first layer of the steel. So primers are generally zinc rich. Keep in mind, you cannot apply zinc rich paint over a other primer and expect that it will work. It will not work. Then inhibition to the surface. When you look at steel surface, and here inhibiting primer is nothing but a zinc phosphate primer. So what happens is, since the coatings when applied are little permeable, it can allow moisture to go and come in contact with the steel. Now, when it comes in contact with the steel, this zinc phosphate reacts with the moisture. It forms phosphoric acid. It again, that phosphoric acid will react with the steel to form ferrous phosphate layer, which is a inert layer. This layer will act as a barrier against further corrosion. So the second method is to use inhibition of steel by using inhibitive primers. Keep in mind, first one is cathodic protection, second one is corrosion protection by inhibition. Then barrier protection, like I was talking to you, a raincoat. Here you apply a thick coat of paint, and that thick coat of paint, because it is thick, will not allow the moisture or other contaminants to pass through very fast. It will delay. So thereby, what will happen is that it will delay the process of corrosion and give the expected durability. So three methods: cathodic protection, inhibition, and barrier protection. When these three processes are added together, that is how they build in coating specifications. How do you protect steel? They will either choose one of them or a combination of these three methods. Primers, it's generally the first layer applied onto steel. It gives you good adhesion, good primary surface protection against corrosion. Keep in mind, it can be inhibitive, it can be a barrier, or it could be a sacrificial coating. Intermediate coatings are generally above primers in order to develop thicknesses. It will have typically these intermediate coats have high thickness building capability, and many of them have this pigment called micaceous iron oxide, which helps in forming a barrier kind of a protection. Okay. In some of the coatings, glass flake is also added to provide the barrier kind of a protection. Keep in mind, finishes is what you see outside once you have completed the coating, the colors, the glass, the aesthetics. So many of the finishes have good, since they are exposed to sunlight, it should have good ultraviolet light protection capability. Otherwise, the paint will fade, it will chalk. That is a coating defect. However, it is inherent to exposure to atmosphere. So what is a finish? Finish is the last coat of paint which gives you the aesthetics. Depending on the requirement, you can use the right coating system to get high level of aesthetics. So when we have understood certain amount of paint, how do we recommend coatings? What is the basis of the specification? Why do you recommend the products in the way it is written in specifications? Because whenever you go to your customers or the customers come to you for paint, they will work on a standard or on a specification. Most universally used coating recommendation standard is called ISO 12944. Now the latest revision has come out in 2008. The first revision came out in 1997. So it has taken 4 iterations to arrive at this level. Every 10 years they keep revising the standard. Now this standard is adapted by the ISO, International Standards Organization, like our ISO 9001, ISO 14001. Similarly, so many ISO standards, they also have a corrosion protection. This is based on a British and a European standard. Earlier, British had a standard called BS 5493 and DIN 55928 in Germany. Both of them were combined together to form this standard. It constantly gets upgraded based on whatever data they get on field exposure. In US, they use SSPC and NACE standards. SSPC is nothing but Steel Structure Painting Council of America. NACE is National Association for Corrosion Engineers. Now, as of the January 1st, both of them have come together. They have joined together called AMPP, Association for Material Performance and Protection. They have come together. So now it will be called AMPP standards. In AkzoNobel, we use this standard as a basis of recommendation while giving internal specifications to customers. And that internal specification is called interspec. So whenever interspec is delivered to our customers, the basis or the standard is ISO 12944. Now, what does this do? It's globally recognized. It was first introduced in 97. It categorizes corrosion based on environment. It has design considerations which will protect such structure by design. Then it gives you insight into surface preparation. It also gives you protective coating systems. What is the thickness? What is the kind of a product? Then how to validate it using lab test methods. It also gives you some insight into how to execute a good practice of executing paint work, painting application. Then how to develop specifications. So I would strongly advise each one of you as a team to have one copy of this for your understanding and recommendation. We can give you a synopsis from our company, but the standard has to be purchased. It's very inexpensive. 30 to 40,000 rupees. It's like Bible, you know. Please take it and read through it. The components are, it has got 9 parts now. Till last revision, it had only 8. In the 2018 version, they have increased it to 9. So the part 1 is general introduction. Second one gives you classification of environments. How do you classify? How do you rate them? Design considerations. Part 4 is type of surface and surface preparation. Protective paint systems, lab test performance requirements. How to execute paint application supervision, how to design specifications for new work and maintenance. Now in part 9, what they have done is protective paint systems and laboratory performance test methods for offshore structures. Offshore structures are very highly corrosive, so they have put a new part there to introduce. This happened in 2018. Till 2018, there were 2 different standards. One was 12944 till C5, that means offshore marine was included there, and they had another standard called ISO 20340, which was for offshore. Now this ISO 20340 has been brought in as part 9, so it becomes a part of ISO 12944. How do you specify? First thing is you should understand what is the durability. How many years does the client want this paint to last? That is number 1. Second one is, where is this fabricated? Where is the steel fabricated? How is transported and where is it finally exposed? You should know that is the environment. Then using part 5 of the standard, you can arrive at a coating system and thickness. Understand? First step is you should refer to part 1, understand durability. Part 2 is understand environment. After that, you can recommend the coating system. Now, when you look at durability, what is the main meaning of durability? Coatings, when applied on steel, you will still corrode the steel over a period of time. Till that time, which is the time before you can do the first maintenance. First touch-up maintenance is called durability. Doesn't mean that when I say durability, lifelong without any problem. You will have some small problems that you have to touch up. What is the minimum period? So there is a standard called ISO 4628 in which rust index 3, that means 1% scattered corrosion is allowed over a period of time. and we have to find out how much time it takes to arrive at that 1% scattered corrosion, based on which they have categorized it as 4 levels. Low durability is up to 7 years. By 7th year, you can expect around 1% of scattered corrosion. Medium is between 7 and 15 years. Between this time, again 1% of scattered corrosion. High is up to 25 years and very high is greater than 25 years. So based on this durability expectation, you can recommend coating systems and thicknesses. Keep in mind. Then environment. There are steel is exposed, it's fabricated in one area, transported through one method and delivered in another area. So environment is classified as C1 is very low, dry cold zone, low exposure to pollution. It's like in a closed air conditioned room you keep a steel object. What is the level of corrosion you will expect? Some examples can be certain deserts, Central Arctic or Antarctica. Just imagine that place pollution free. You know, deserts are pollution free, central deserts are pollution free, nobody will live there. So such places in a controlled substrates, C2 is low, temperate zone, atmospheric environment with lower level of sulfur dioxide, dry cold zone with very low wetness, short time of wetness. Medium is C3 is temperate zone. For example, C3 can be somewhere in the middle of Bangalore city. Little effect of chlorides, some amount of exposure to pollution, but not very corrosive. C4 is high. For example, when you go closer towards any industrial area, any power plant, any refinery, that place is very highly polluted, is it not? Sulfur dioxide from stacks, nitrous oxide, equipment, material movement, those are very highly polluting areas. So when you expose yourself to pollution, the rate of corrosion increases. Such locations are called C4 environment. C5 is atmosphere with very high level of pollution, significant exposure to chlorides, industrial areas, coastal areas, sheltered positions on the coastline. For example, anything, a coastline of Mangalore, Mumbai, coastline of Colombo, you could call coastline of Chennai, Visakhapatnam, any of these places, Gujarat, these are C5 environment. Then CX extreme is, this is a new environment. This is offshore. In offshore, you will have specific structures where you have manufacturing FPSOs, where you refine oil offshore. Those places will have higher sulfur dioxide extent, constant exposure to salt because of the sea mist. So the rate of corrosion increases. Look at very low corrosion to CX. No, the rate of corrosion, the impact of corrosion increases. That is atmospheric exposure. Now, when you look at immersion exposure, you have 4 levels, IM1 to IM4. IM1 is fresh water, river installations, hydroelectric power plants. IM2 would be sea and brackish water. That is without cathodic protection. That additional zinc anodes or ICCP wouldn't be provided. IM3 is buried in soil. For example, pipelines buried in soil. Structures which have a soil contact. Buried tanks, steel pipes, steel columns which are buried in soil. Then IM4 is immersion in sea in brackish water with cathodic protection. For example, immersed pipelines, subsea pipelines. It is in seawater. At the same time, they are provided cathodic protection. That is IM4. So if you look at C1 as the lowest level of corrosion possibility, IM4 is got the most intense level of corrosion possibility. Based on which and durability, you recommend coating thicknesses. For example, environment for C1. C2 inside an airport, stadium in the midst of a city, C3, a power plant, this is C4, offshore structure C5, C5M. Now when you specify coating systems, when you look at this standard, it clearly gives you the binder type, what is the resin type you got to use, what is the number of coats, what is the nominal dry film thickness you got to apply, and what is the durability. Here you can see the durability. For example, for C5, that is marine coastal environment, if you want a durability of very high, greater than 25 years, you should have this coating system. An epoxy primer or a polyurethane primer of 80 microns, epoxy subsequent coats of epoxy, polyurethane or an acrylic leading to 240 microns. 240 minus 80 is 160 microns of intermediate coat. Okay. So total number of coats would be 1 plus 3, 4 coats. So if you have a coating system and this is applied on carbon steel after abrasive blasting and proper cleaning, then the durability can be greater than 25 years. Do you understand? But look as you go up, the same environment C5, if you want lower durability, then it will be 160 microns. So that is how it works. Now, when we look at application processes, it's very important paints are applied properly. What are the methods of application? Brush, roller, conventional, airless spray. Simple, not many things. How do you use? Which one to use? What is the paint to be applied? Is it fast drying? It has got aggregate. What is the substrate? Is it small, complex? It's large areas. What are the environmental considerations? Is spray application allowed in those areas? What about overspray and other work conditions? What about transfer efficiency? What about wind conditions? How much paint will be deposited? What is the cleanup? Is it difficult to clean up after application or not? So based on that, you will look at it. Now, application brush, simple. It looks simple, but not as simple. Quality of brush is important. It should be made from bristle, not nylon, because solvent-based paint, you should be very careful. Best quality brushes, I would look after them properly. Brushes are preferred over rollers for high build in order to build thicknesses. It is working, it should be worked methodically and quickly. And coverage is around 100 square meters in a man day. So smaller jobs you can do with brush and on roller, faster. That means 200 to 400 square meters. But you cannot reach all all areas. There you'll have to do a combination of brush and roller. Rollering doesn't require skill. It's a very mechanical job. Typically lower thicknesses are achieved, 40, 60, 70 microns. Quality of roller is very important. Otherwise it will leave surface finish issues. And roller is typically once you brush apply in order to finish, you roller it. You would have found it in your house on walls also. That's the way it is done. Then conventional spray. This is the gun which you normally see for automotive painting and all that. Yeah, in which the air comes in contact with the paint, it forms mist and it is applied on the. It's a simple gun which you find. It has got an air inlet. It's got a trigger. Paint comes in combination. It has a fan which or a spread because of the air pressure and it's applied. This can be applied at around 500 square meters a day. Thicknesses will not be very high. You can build up to thicknesses of around 60 to 80 microns. And more importantly, when you apply by conventional spray, you have to thin the paint. So thinner consumption will be very high. In high performance coatings, you use conventional spray, especially to apply inorganic zinc silicates with an additional equipment called the pressure pot. Because zinc will be heavy material, it will settle down. You got to mix it continuously. So you use something called a pressure pot. Keep in mind, airless spray is the most predominant method used for applying coatings in high performance. That is the business we all get into actually. Airless spray by its name says that air is not coming in contact with paint. It will only run the pump. That's all. The paint goes through a very narrow orifice and it makes a fan. It sprays itself. It atomizes and it's called airless. Airless spray equipment are very high pressure equipment. They are pressure multipliers. The initial pressure at the pump suction to the final pressure at the gun tip could be multiplied by 30 times and 40 times and 60 times. Now 73 times also. Depends on that. Advantage of airless spray is it can take very thick paint and deliver very high thicknesses. Productivity will be very high. For example, you can develop thicknesses up to 2 mm and 3 mm using a single spray. But they are very high pressure equipment. It's also got its own safety challenges. Specialized applicators do this job. Keep in mind. For example, the pump looks like this, it's got a pump, it's got a suction, and the spray gun looks like this. The orange one is called the tip guard. It's the safety part of the gun. So if you should not get anywhere close to this, because if you get close to the tip and you spray, the paint can go into your body. It can inject into your body. You may need amputation. So normally when airless spray is applied, we stay at a distance and we also ensure this tip guard is in place. That is a safety component. These are multiple methods of coating application. When you apply coatings, you will apply very well. Otherwise, sometimes you get defects also. It happens because coating application is a manual job. Flaw that spoils the required appearance or specified performance is called a coating defect. Types of defects, blistering, bleeding, poor coverage, loss of gloss, loss of adhesion, wrinkling, all these things will happen. Overspray, dry spray. You can find rash rusting because of poor coverage, pinholes, cratering, chalking. You could find sags and runs, sometimes a rough orange peel like of a finish. So you have to observe very closely in order to detect defect. Special eyes are required for this. In the sense, experience is what I say. Everybody can detect once experience is there. Causes of coating defects, it can start from poor surface preparation, surface contamination, higher surface profile, poor application, improper mixing, use of brush and roller improperly, low and high DFT, overspray, dry spray. Then it could be due to incorrect paint systems. Instead of using a 2-pack system, used a 1-pack system. Incorrect system for the environment. For example, for a C5, used a C1 system. It will naturally fail. Some of the objects are designed very poorly, poor access to coatings. So such places will have issues. For example, stitch welding. You would find welding in parts on a structure. The gaps will lead to corrosion. So keep in mind these are areas. Then poor quality of paints. Sometimes the paint can also fail in a manufacturing in its formulation. Even that can cause coating defects. In terms of, I'm giving you only examples. Coating defects, there is a book of 1,000 pages. I cannot share it here. I'll share some of the examples. Blast profile, in abrasive blast, if the profile is much higher and the coating thickness is lesser, the top of the peaks will be exposed and such areas are called rash rusting. So you should moderate the profile. This is a defect which comes out of surface preparation. Keep in mind. Sissing, where air is entrapped in the profile and it comes out as the paint dries. So it will remove small popping marks in the surface, like very small craters. That is nothing but sissing. Surface contamination, presence of oil and grease on top of the surface also causes sissing because oil has got lower surface tension and it will never allow the paint to adhere. It can come out on the surface. So that is an issue. Then mill scale effects. For example, I said steel, when it is exposed at a high temperature, it forms a bluish black oxide, which is mill scale. Mill scale is non-metallic, it can crack. So that detachment will lead to galvanic corrosion. It will lead to delamination. Keep in mind. Welding issues, I was talking to you on weld flux, stitch welding, weld spatter provided on steel. All these things need to be removed. If you apply paint on that, those areas will be loose. It will come out at a later date and start corroding. Blooming, amine bloom is the reaction of component of the paint, which is part B, an amine adduct to the air and moisture before full cure, which will form a milky kind of a finish on the substrate, which will not react, but it will also be very streaky sometimes. So it is not detrimental. It will close it at any point in time. Of course, blushing is also there, which forms a white surface. Then you have dry spray application issue, where the paint flows into the other areas, thereby causing issues in terms of drying of paint droplets in other areas. So I have shared a few defects only. It's an elaborate one. So if I have more time, I could spend hours together on this. I'm limited on time. I'm sorry for this. With this, I end my webinar and I'm open to questions. The moderator will take the questions and share it with me, and I'll try my best to respond to you guys. Akshay, over to you.
Thank you, Badri. Thank you for your informative session.
Yes.
We have quite a bit of questions from the participants here.